Standing waves occur when there is resonance. And so what happens is if we send two waves at each other, two waveforms at each other, and they meet in general, where they meet, they would add up on each other. And if we were to do this repetitively, if we had lots of waves coming and lots of waves coming, they would continue to add up. And what that would look like is what would give us a standing wave. So this one would add to that one would add to that one, and we'd see this pattern of the waveforms adding up. And that's what we're dealing with when we have a standing wave. And standing waves occur when there's resonance. Resonance and standing waves kind of go together. And what happens is the wave builds up to create nodes and antinodes. And I'll show you that in the drawing that we have in a moment. And it's because it's repetitive waveforms that are falling exactly in line with each other to add up every time. And when we're dealing with the idea of sound, this is where it gets louder. So this is a big thing in designing and building instruments. When we talk about nodes, nodes will be the spot where there's no movement, and antinodes will be the most movement. So we might see this in way of a string. And with a string, we have nodes at both ends. You can send a lot of frequencies along the string, but the only time it will resonate and continue to build up is when you have a node at both ends. So there's a few different ways that this can show up. If I go from the first node to the second node, it ends up looking like this. That would be the part of the wave, and then it would flip down like this. Because this is only the up part and it flips back and forth, this would be 1/2 of a wavelength. On this same string, I could force it to go from here's the wave. So I've got one wavelength, but as it builds up, it'll flip back and forth on each other, and we would get it to look like this. So when you have waves drawn something like this, it's indicating that it's a standing wave and that you've hit resonance. So I still go from a node to a node. I have another node in the middle though. On this one, same idea. I have a node and a node. I have two nodes in the middle. So if I look at this wavelength, I've got half a wavelength here, a half here, and a half here. So I have 3 halves, or 1 and 1/2 of a wavelength. And this is how it shows up in a string. Now the same thing happens in a tube. There's two types of tubes that we'll deal with. One of them deals with a tube that's open at both ends. With any type of tube, an antinode falls at an open end, and a node falls at a closed end. So because both of the ends of this tube are open, we'll have an antinode at each end. So the way that would be drawn is I'm going from the peak of this wave down to the trough on the other side, and then I draw the mirror image of that showing how it flips. So I have an antinode here and an antinode here, and this also is just 1/2 of that wavelength. If I look at the wave, part of it would actually start here and part of it would actually continue here. So I'd have a fourth here and a fourth here, and half that would be in the tube. This next one that would meet the requirements of an antinode at each end looks like this. So I have an antinode and antinode. I end up with 2 nodes in the middle. And this ends up giving me 1 full wavelength. If I follow the wave and I start here, and I start at the peak, I go down, I end at the peak, that's 1 full wavelength. And the mirror image of it is just showing how it flips up and down. The third time that this would happen would look something like this, where I have, again, antinode at each end. I've got 1 1/2 waves here. It's following the same pattern that we had with a wave on a string. Both of them go 1/2, 1, 1 and 1/2. The wave on a string starts at the nodes and ends at the nodes. This is shifted to be antinode to antinode here, but the pattern is the same. The third type that we'll deal with is a tube that's opened at one end and is closed at the other. When we looked up here, antinodes are at the open end and nodes are at the closed ends. So this one will start with a node here and we'll end with the first antinode. Now this is a very small portion of the wave. The wave itself would come up, go down and then up, would be about that long. So at this point, the amount of the wave that's in the tube is only 1/4 of a wavelength. If we go on to the next one here, we go up and end here, down and end here. We start with a node, we end with an antinode, and this gives us 3/4 of a wavelength. This is half, and then this part is 1/4. If we come down here, do the same thing. We go up, down, and up. Same idea, we start with a node, we end with an antinode on the open end, and here we end up with 5/4 of our wavelength. And this could continue with more tubes if we wanted it to. There's equations that go along with these as well. We'll go back to the string here. When we're talking about the string, our equation looks like this. We say f of n, and that's a subscript. That's not something that you'll actually do with the number. It's just indicating what n you'll use, and I'll talk about that in a minute. Equals n v over 2l. In this situation, n can only be 1, 2, 3, etc. It can be 4, 5, 6. It has to be a positive whole number. And what this does is f is the frequency, and frequency is measured in hertz. V, in this case, will be the speed of sound in the string. And that's going to vary based on the temperature, based on the tension, based on what the string's made of. But the speed of sound in that string will be the V that we have here. And then L is the length of the string. And this has to be measured in meters. If it's in centimeters, you'll need to get it into meters before you calculate. This N value goes in here. And what it does is it gives us what we need to meet the criteria of having a node at each end. And so if I say N is 1 and I put the 1 here, I have 1 divided by the 2 there, and I'd have 1/2 of my wavelength. If I take N of 2 and put that in here, I'd have 2 divided by 2, and I have 1 of the wavelength. 3, I'd have 3 divided by 2, so I'd have my 3/2. That would give me 1/2. And I could continue with other values all the way down. I could say 4, 5, 6, 7. The only thing that'll happen is if you're dealing with sound, they get really, really quiet as you do that. So with a string, you have this equation, and you're dealing with this type of setup. Now, earlier we said that when you're dealing with a tube that's open at both ends, it has the same pattern as this string. And so it actually has the same equation with a couple of differences in it. So we can say that f of n equals nv over 2l. In this case, it's the air that's vibrating in the tube that gives us that sound. And so this, we say, v is the speed of sound in air. If it's not given, you can use 340 meters per second. But the speed of sound in air does depend on the temperature of the air. So sometimes it might be 343, or it might be down to 335, or various types of temperatures would change various speeds. So if it's given, use that. If it's not, you can use 340. This is the length. I can't spell, of the tube. And in this case, again, it has to be in meters. If it's in centimeters, switch it into meters. Again, n is going to equal 1, 2, 3, etc. It'll give the same pattern. And F is your frequency in hertz. So if you're dealing with a tube that's open at both ends, you're dealing with this equation where n equals 1, 2, and 3, or continuing out, and you have the speed of sound in air for the velocity there. Changes a little bit when you're dealing with open at one end because you have a different pattern here. And this one looks like this: f of n equals nv over 4L. And if you, in this case, the n can only be odd numbers, so 1, 3, 5, etc. If you take 1 and put that in for n, you have 1 over 4, so you'd have the 1/4. If you take the 3, put it in for n, you'd have 3 over 4, 3/4. 5 would be 5 over 4, 5/4. So it follows that pattern of what the waves would look like. Again, you have your frequency in hertz. You have your n values that are here. You have the speed of sound in air. And you have the length of the tube in meters. Just like that. A couple examples that can be helpful with this. If we take example 1, we have a tube is open at both ends. It's 25 centimeters long. Calculate the first 3 frequencies that will resonate in the tube. So our length here is 25 centimeters. We cannot leave it as centimeters. We have to get it into meters. So 0.25 meters. There's no speed of sound given, so we'll use 340 meters per second. We're looking for the frequency, and we're looking for our first 3 frequencies. So because this tube is open at both ends, we'll say f of n equals nv over 2L. And the n's we can use are 1, 2, 3, etc. So these are the first 3 frequencies that we have. So we'll use n equals 1, 2, and 3, and we'll do that 3 different times. So we'll say f of 1 equals 1 times 340 over 2 times 0.25. Now, if you're putting this in a calculator, you need to make sure that you keep this in parentheses for order of operations to be followed. So if you take 340 divided by this, you end up with 680 hertz. That would be for your first frequency. We call this the resonant frequency. We'd go to F2. We'd say that's equal to 2 times 340 over 2 times 0.25. And on that one, we end with 1360 hertz. We do it a third time for F of 3. We get 3 times 340 over 2 times 0.25. And here we get 2040 hertz. So if they're asking for the first 3 frequencies, you'll take the first 3 n values that are available. In this case, it happens to be 1, 2, and 3. Another way we might have to solve this is dealing with solving for the speed of sound in a string. And so in this case, you have a string has a length of 0.45 meters. It's already given in meters. You don't have to change anything. It plays an A note, which is 440 hertz. And you're calculating the speed of sound in the string. Because nothing is given about your n value, you can assume that n equals 1. So we have these variables here, and we're going to solve for v. Well, v is up here on this side. So I need to multiply both sides by 2L to get rid of the 2L there. So I have 2L times f of n equals n times v. And I'm going to divide by n. Cancels out here. It does not cancel out here. This n is just a subscript. And so we'll just leave that there. It doesn't do anything to the number. It just indicates what n value you'd be using. So because of this, we have v equals 2L times f of n over n. And so we can say 2 times 0.45 times our f of n. So f of 1, we'll use the 440 here, divided by 1. And when we do that, we get 396 meters per second would be the speed in that string.